Contigo en la distancia estoy.
Simultaneous translation service. So that people can switch between languages. But they charge like $700 for this thing. And, yeah, I mean, that's could be nice, but I don't know.
Ya estamos en vivo.
Ok, cuento 10 y inicio la presentación.
Ya puede iniciar, ¿eh? Ya.
¿En YouTube también?
Sí, ya.
Perfecto. Good morning in the Americas, guten Abend in Deutschland, buenos días en América. Welcome everyone, bienvenidos todos to the International Seminar on Language, Culture and Cognition, also known as the LCC International Seminar, as part of the series from the National Coordination of the National Institute for Anthropology and History. My name is Alberto Avellino. On behalf of my colleagues and friends co-organizers of this seminar, Rosalía Rodríguez Vázquez, Frida Villavicencio, Damián Blasi, and Harald Baayen. We are broadcasting on YouTube too, so please remember that you could switch on your captions to your preferred language on the YouTube broadcast. I would like now to introduce to our keynote speaker, Professor Dr. Harald Baayen. Harald is the Director of Quantitative Linguistics Group at the University of Tübingen in Germany. Many of you already may know, have heard about Harald Baayen. He is with no doubt one of the leading figures in contemporary linguistics. Harald Baayen has a doctorate from the University of Amsterdam. He has worked at the Max Planck Institute for Psycholinguistics. After he had an appointment at the Radboud University in Nijmegen from 2007, he was a professor at the University of Alberta, Canada. In 2010, Harald received the Humboldt Professorship, a really prestigious professorship, which he has held at the University of Tübingen since 2011. Harald Baayen is really one of the main figures in the development of contemporary quantitative turn in linguistics. As a token of example, his book, Analyzing Linguistic Data, A Practical Introduction to Statistics Using R, is one of the most used textbooks in linguistics and related disciplines. He's also well known for his contributions on memory in language processing and computer models for speech recognition. Harald's recent research has dealt with morphological processing and modeling together with language variation and the implementation of statistical analysis of language data. One of the most prominent features of Harald, to me, is that Harald is an original thinker. The first impression I have from Harald is he's a thinker. He's original, he's a pioneer, he likes to go to places where no one else has been before and questioning everything. So questioning the already established knowledge to further really our knowledge. So without further ado, I give the floor to Harald. Harald, please, this virtual floor is yours. By the way, we're in the same room in Tübingen, Germany, and I will give you the floor. Harald. So let me unmute myself so that we don't have a loop, and you can start now.
Good. So I am assuming that people can hear me. And
okay. So thanks, Roberto. It's great to have you here in Germany. And the topic that I have for this afternoon comes with the title modeling lexical processing with linear mappings. I've been kicked out.
Oh, good. Okay.
Yeah, you take off your phone. I don't know what this is. I will. Right. Yes. Look. I'm going to check this.
Yeah. Let's see. What then? And I can give you access or people then. Oh, really? Well, I'm wireless and works fine.
Yeah, I want. Maybe should try. Try the wireless. Not sure if that is bad.
So I'd say something
Yeah, I
to
would say
the
something that.
Greetings, greetings. It seems that we are experiencing technical troubles here, so but we will be fixed in a second. Just hang on, please.
So it looks like I'm back. Sorry for this trouble. So now I need to share my screen. And that means that good. And now so good.
Okay.
Yeah,
They just confirmed that your sound is fine.
Yeah.
Should be.
Okay. So then let's hope that my computer doesn't crash again. Okay. So what I would like to talk about this afternoon is what we can do when we think about the lexicon and the mental lexicon with the representations that have been becoming popular in natural language processing, namely what are called semantic vectors or word embeddings. So high-dimensional numeric representations of words' meanings. So when I got interested in morphology, these things didn't exist. So you could set up relations between words' forms and their meanings, typically represented by words in capital letters or underlined or with a prime. And we have notation for morphosyntactic features like present or past or future. But then basically a lot of what morphology revolved around is looking at how you can get from one word form to the other word form. And now that we have much more subtle representations of what words mean, we can look at the relation between form and meaning in a more direct way. And that is what I have been trying to do over the past couple of years, using the simplest, mathematically, the simplest possible way of moving between form spaces and meaning spaces. So in an approach that I sometimes like to call the discriminative lexicon approach, what we do is that we try to represent words' forms by numeric vectors. So here you see 3 English words, cat, dog, and cut. And on the top, you see letter pairs where the hash mark denotes word beginning or word end. So the word cat is now represented by 4 bits on for the 4 diphones that are in the word cat, and all the others are 0. Similarly, if we go to dog, then the diphones for dog are on and all the others are off. There are other ways in which we can set up these kind of form vectors for words. We have a method for doing this also straight from the speech signal, but we'll keep it simple and we look at these form representations for now. So every word is now coupled with a high-dimensional vector consisting of 1s and 0s that specify which diphones are present in that word. Then we can use the embeddings or semantic vectors from distributional semantics. And then for the words cat, dog, and cut, we get vectors with real numbers in them. And the dimensions of these vectors typically don't have a clear interpretation. However, if you compare the vectors of cat and dog by looking at the angle between them, then typically you will find that the angle between 2 vectors is smaller if the corresponding words are perceived by us humans as more similar in meaning. Now, what we can do if we have form representations in a high-dimensional space and we have semantic representations in a high-dimensional space is that we can start moving between them. So here you see a vector for form, a matrix with vectors for forms. The row vectors are, in this very simplified example, specify words forms, and here we have semantic vectors that specify words meanings. These row vectors can be represented as the vectors A, B, and C in this plane, and these semantic vectors can be represented by the vectors A, B, and C in red in the right plane. And the interesting thing is that there is an operation known as simple matrix multiplication that can take the vectors in C, the blue vectors, and transform them in the red vectors. And if we have the red vectors, there is an inverse mapping G that will take the red vectors and put them back as the blue vectors. That's the basic idea underlying everything that I will be talking about this afternoon. Now, when we think about the mental lexicon, then that is an almighty complex system. We have semantic vectors, but then we can have auditory form vectors derived from the speech signal, or we could have visual vectors derived from the visual input. We may want to speak, and then we need to have some numeric representation for speech, or we might want to write, and then we get different vectors for driving the muscles for writing. And then between, So then we have these simple mappings of this type that take us from a visual vector to a speech vector, or from a visual vector to a semantic vector. So for instance, in reading for English, there's a lot of evidence suggesting that there is a direct route straight to the semantics, but there's also an indirect route through the phonology that takes you through the semantics. Okay, so the big picture is quite complex. What I will be looking at are a couple of case studies that each of them are a lot simpler. But before I do that, I need to say a few things that if we make a mapping from form to meaning for comprehension, or from meaning to form when we're talking about production, then we also need to know how good these mappings are. So for comprehension, this is fairly straightforward. If we have in our space of our semantic space in the mental lexicon, we have the 3 blue vectors for fish, cat, and dog. And then our mapping from some form ends up to be the red vector, then the most likely meaning that we will choose is fish. Yeah, this might be wrong, but this vector, the red vector, is closest to the blue vector for fish, and hence we select fish as the word that is recognized. When we look at production, the result of the mapping from meaning to form results in a bag of triphones or diphones in the example I gave above. And these are unordered. So we need some kind of mechanism that orders the diphones in the proper way. And for that, we have a set of mappings that take the predicted form vector and that learn what positions are most likely. And on the basis of that information, several word candidates for production are estimated. Can you close the window? And then what we do is that going first from the semantics to a set of form candidates, we then select that candidate that when we map it back to the semantics, best matches what we are trying to say. Okay, so we can look at this very simple approach as a kind of simplified connectionism. We have got rid of all hidden layers, but we do use numeric representations at the form and the meaning level. It's other than connectionism, this is also more a statistical approach rather than a machine learning approach. The mathematics that we are using are basically the mathematics of regression analysis. And the key point is that what we can now do is integrate insights from distributional semantics and natural language processing into a computational model of lexical processing. Now, I have 3 case studies that illustrate why I am enthusiastic about this approach, even though I am also acutely aware that it has many limitations. And the first study goes back to earlier work by Susanne Gall, who in 2008 published a paper with the title "Time and Time Are Not Homophones: The Effect of Lemma Frequency on Word Durations in Spontaneous Speech." She observed that low frequency time tends to have on average a longer duration than high frequency time. We now can ask, are differences in the meanings of homophones co-determining their spoken word duration? What Susanne Gall tried to establish in 2008, and I think pretty convincingly, is that frequency is a good predictor of homophone duration. But is it only frequency, or is more at stake? And as long as you just talk about homophones as words or as symbols, then there is very little that we can do with them other than say that they sound roughly the same, but differ in meaning. But maybe there's more that we can say about the duration, the spoken word duration of homophones, when we start thinking about the meanings of these homophones using distributional semantics. So here is a research question that she and I have been working on, namely, which theory predicts spoken word duration with more precision? Localist theories, in which we have symbols for words and subword units, or a kind of discriminative theory that uses distributional semantics to link form to meaning? Now, if you take her data on homophones, then there are, of course, a lot of predictors that we have to think of, like local speech rate. If somebody is speaking quick, even long herb time will be pronounced short. So speech rate has to be taken into account. And you can think about forward and backward conditional probabilities, disfluencies and pauses, where you are in the phrase, in the beginning or at the end. Is a word used more often as a noun or a verb? All these things are known to influence spoken word duration. And then in a localist approach, as you see illustrated here, You can work with semantic features. Then you have word nodes, you have onsets, vowels, and codas. This is a late model of Gary Dell and his collaborators. Then these are the units with which we have to explain things like reaction time. So we can look at neighbors, we can look at length, we can, and then we come up with predictors like the frequency of use of word units, the relative frequencies of homophone word units, number of neighboring word units, phone unit duration, phone unit combinatorics. All these kind of predictors come into play. What you see here is a visual summary of a model that we fitted to the acoustic durations, the spoken word durations of the homophones in Susanna's data set using a Gaussian location scale generalized additive model. So this is a model that models both the mean and the variance at the same time. And it is a model that can handle nonlinearities. Now, here you see the effect of a following pause. If there is a following pause, the word is longer. If the phonological neighborhood density is high, the word is shorter. There is a small effect of orthographic irregularity. This is a measure that is dear to Susanna's heart. It's residual. It's a kind of baseline duration of the phones, has a strong effect. This is the effect of frequency on the variability. So for higher frequency words, you have less variability in their duration. And here you see a frequency by on the horizontal axis, and on the vertical axis, you have the ratio of the frequencies of the homophones. In this plot, the red line connects points that have the same predicted value, and green means shorter RT, and this dark yellow is longer RT. You can see that there is some interaction of frequency by frequency ratio. Okay, this is the pattern of results that we get out of her data when we look at it with these beautiful statistical models. Now, let's look at what we can do when we try to bring into the analysis this idea that we can do something with word embeddings, with these semantic representations, these high-dimensional semantic representations for meanings. So here I have a very simple toy example, 2 words, time and line, their form vectors, and then here some faked simulated semantic vectors. And what we can now do is we can say, okay, we find a mapping G that takes us from the semantic vectors to the form vectors. Yeah, so this is trying to model production. We start with the semantic vectors, we try to get to the form vectors. And if I do that, then I get these numbers out. This is such a simple toy example that they can move from the semantic vectors to these form vectors with enormous precision. This is a bit boring, so I will just assume that the actual values might look more like this. And this is what you could see in the kind of data that we have been working with. So you can see that for time, I'm, and m, you have fairly large values, and for the 2 triphones that are not in the word, you get little support from the semantics. For line, on the other hand, you don't get much support for ta and time, and I, but you do get support for the other 4. What we now do is that if we are interested in time, we can look at the total support that the triphones that are actually in time, so that is these first 4 blue triphones, we can say we can take their support that they get from the semantics and add it up. And this is what we will call the semantic support for form. And we will use that as a new predictor for spoken word duration. We also looked at the semantic similarity of the homophones. So if we take the vector for time and the vector for the other time, and we look at their correlation or their cosine similarity, then we can say, does this make a difference? Whether the two words are more or less similar in their meaning. Now, there's one thing that is a bit of a problem, and that is, what do we do with word frequency? Because in this model, there are no word units to which we could attach a frequency count. We have input form vectors, and those form vectors generate dynamically with this very simple network or this very simple matrix multiplication. They generate a semantic vector. So at no point is anything retrieved from something like a paper dictionary. We generate meanings when we listen, we generate forms when we speak, but there are no intermediate representations. But we all know that frequency is a very strong predictor for all kinds of things: spoken word duration, reaction times, naming latencies, and so on. So how do we bring frequency into the model? Well, what we did is we made our own word embeddings by taking a very simple network, sentence by sentence, through the utterances in the British National Corpus. And we taught this very simple network to predict all the words in the utterance from the words in the utterance. Now, words in this setup are also allowed to predict themselves. This is something that systems like Word2Vec do not like. But we did this, and we can call this the self-predictability, and its values range between 0 and 1. So you can look at this as a kind of frequency measure that is modulated by how many other words a word co-occurs with. And we can take the negative log of this, and then we get an amount of information measure. Here you see on the horizontal axis log frequency. On the vertical axis, you have the log of this information measure. And you can see that the two are correlated, although it is not a linear relation. And this particular way of looking at frequency seems to do a fairly decent job. If we look at the correlation of RTs, or we model RTs in a large lexical decision data set, we can predict RTs from frequency, and we can predict it from this information measure. And then it looks like prediction with the information measure does a better job. Okay, now, what are the predictions that you get from the two kinds of theories? So on the one hand, the classical theory, where we work with frequency, you would say high frequency words are not very informative, and hence they get a short duration, and low frequency words have a high information load and hence get a longer duration. This is one of the central ideas underlying the paper by Harald and Turk from 2004. Okay, now that's very nice work. I think there is a lot of truth to that. But let's look at what happens when we think about the semantic measures. So we have this semantic support for forms, so the total support that a word's triphones receive from the semantics. And then what we predict is if there is more support for the semantics, we get longer durations. Yeah. Conversely, if there is no support for a triphone, you shouldn't pronounce it. It should have 0 duration. So that's the logic behind it. Yeah. The more support there is for a word's triphones, the longer the word will be realized. And then when we think about greater homophone semantic similarity, yeah, so if the two homophones are more similar in meanings according to the word embeddings, then what we expect is that we get longer durations. And the reason is that if they are more similar in meaning, then you get closer to a good one-to-one mapping between meaning and form. That makes the mappings as we do them with very simple linear transformations. That makes these mappings less frail, so you get more support at the form side, which again implies longer durations. Now, this is the model that we get out with the predictors that I just introduced, including some important control predictors. So, pauses are here. Here is this baseline duration. Here you have our frequency effect. This is telling us that if there is more information, so lower frequency words if you want, then there is more variability. But what is interesting to see is that homophone similarity. So if two homophones are more similar in meaning, they become longer in duration. And that here we see that the semantic support for the form is a strong determinant of the spoken word duration, with a similar order of magnitude of an effect as the frequency effect that you see here. Now, if you compare the two models, the model with the classical predictors and the model with our new semantic predictors, then you see that the AIC for our model is a little bit lower. And another thing is the model with the classical predictors had lots of nonlinearities, whereas in the LDL model, we only have linear effects. So we have a simpler model that works better. So what do we take home from this? Well, meaning matters for spoken word duration. And perhaps phonetics might benefit from distributional semantics. My second example is a bit different. We go to noun plurals in English. And this is work that I've been working on with one of my students, Elnas Shafai Bayestan. So what you see here are apples and oranges. And we're going to compare them. But the research question underlying this comparison is, how do we model conceptualization for inflection? One popular idea that we proposed in a paper a couple of years ago, but that's also popular in the natural language processing community, is that if you think about something like plural, then it means that you make a constant shift in semantic space. So if the blue dots are singulars and the red dots are plurals, then going from a singular to a plural is a fixed shift of the same length and the same orientation for all singulars. Yeah? And this fits very well with the idea that we say, okay, what is a plural? Well, a plural, the meaning of a plural is the meaning of the singular plus the addition of some idea of plurality. And how the plural works out is the same for every word that it is that is input to the pluralization rule. However, it turns out that if we take the word embeddings that we get from our colleagues in computer science seriously, then adding a fixed vector to go from a singular to a plural turns out to be too simplistic. And I will illustrate this for the English noun plural. So the basic idea is that if I have the word pen, then I have a shift vector such that I end up at the word pens. So I start at pen, then there is the plural vector that makes sure that I end up at the meaning of pens. And this can be formulated as a proportional analogy. So you could say pen is to pen plus plural, as table is to table plus plural. Okay, now we can look at those shift vectors. And here we are representing these shift vectors in one way. Here we are looking at the angle of the shift vector with one of the basis vectors of the space. And vertically, we have the length of the vector. Now you can see that we have an enormous variability in the shift vectors. And the average shift vector is this poor, lonely red dot. It's sitting way outside of the crowd of actual shift vectors. Now that's not good. If this is what we are adding to a singular to get the plural, then we are basically off for each and every word. Now, what we do here in this plot is that we take the shift vectors and we do a dimension reduction using stochastic neighborhood or t-distributed stochastic neighborhood embedding. The technique is not very important. It's a popular technique in computer science nowadays that is supposedly optimal for finding clusters if there are clusters. So this is 5,000 shift vectors for English. And the coloring is by top categories in WordNet. What you see here in purple, for instance, are a cluster of words for persons. And over here, this is a cluster for animals. And here you see a cluster for plants. So it looks like there is semantic structure to the way in which we make plurals. I'm just zooming in. You can see there is clusters again. There's also a huge spread. But here in green, you have buildings. In orange, you have ways. In red, you have conveyances. In blue, you have what would be pieces of clothing. And then here we have some musical instruments. But you can also see that there is a wide scatter, but there's also clustering. So this leads to a model where we say, okay, how can we think of a plural vector? Well, we maybe need to do the following. Take the meaning of the lexeme, and then we add a plural vector, a plural shift vector that is conditioned on the semantic class. And then there is probably some stuff that is word specific that we're not getting with these kind of very generalized operations. So if we now look at fruits, apples and oranges again, the idea is, hey, okay, these are both fruits, and in the plural, you stack them in roughly the same way. This is a natural way of encountering apples and oranges. If we then compare oranges and elephants, the elephants occur in a very different kinds of configurations than do the oranges, so that we have a very different shift vector for animals as compared to fruits. Makes sense. But we also need this error vector, because here we have some dogs and elephants. And for dogs, we're perfectly happy with these being very different breeds of dogs. But elephants typically occur in herds with the same species. So there are very species-specific aspects to words' meanings, and that is then what we try to represent with this error vector. Now we can look at how well do these kind of vectors work, and then, well, yes, if we build vectors, estimate what vectors should be using empirical vectors, but decomposing them in this way, then we are pretty accurate on training data and even pretty accurate on test data as well. Now, there are other contenders on the market for how you could model conceptualization. For instance, there is the model by Morelli and Baroni, their so-called FRAX model, which says we make a linear mapping that is estimated on all singular plural pairs. And the pluralization operator is then understood as applying this linear mapping to go from any singular to the plural form. So in this kind of setup, all the given plural form is informed by all the singulars in the data set. The method that I just illustrated conditions on the semantic class, given the cluster analysis of the shift vectors. So then we can ask which method for conceptualizing plural vectors works best for the comprehension of unseen data. And then we can compare the two methods, the conditional method on the left and the method of Morelli and Baroni on the right. The dark blue bars are concerned training data, the light blue bars, the test data. Basically, we only need to look at the very left most 2 bars, they concern where the model got it correct. The next are, is the correct target among the top 2, the top 3, the top 4, etc. You can see that on the training data, the models do very similar work, but on the test data, the held out data, the conditional model is what you could call more productive. And in some more recent work that I will not discuss in detail here, we can see that if we do this with the real audio, then this difference becomes even more pronounced. And then it becomes even more important that we really take into account that the semantic class of the base word is a strong determinant of what the plural vector should be. So, conclusions of this little case study: pluralization is more than just adding the feature plus plural. And it also looks like form and meaning are actually quite beautifully calibrated. My last study for this afternoon looks at trial-to-trial learning. We know from priming experiments that just listening to one word or reading one word can affect how you perceive the next word. It's even so bad that if you first see a grand piano and then have to say the word table, that you are slower in saying the word table in that condition than when you first see a ball and then the word table. And the reason is that the features that a grand piano, the visual features that a grand piano and a table have in common are affecting learning, such that, say, having a flat surface is now a feature that will strengthen after having seen the grand piano. It will point to grand piano with a greater value, and it will be downgraded as a feature for table. This is work by Marcelac, and it just illustrates that our categories are not fixed. They are continuously recalibrated by our experience. Now, what we are trying to do in this study, which is done with Maria Heitmeyer and Ying Chang, is to see whether we can see effects of trial-to-trial learning within experiments using this kind of regression approach. So here you see the first couple of words that come in a big lexical decision experiment carried out in English, where there were almost 80 subjects who were doing 16 hours of lexical decision each. So this gives us lexical decision, visual lexical decision data on almost 30,000 words. Our questions are, do we see trial-to-trial learning taking place in this experiment? And the second question is our very simple modeling approach able to detect this ongoing learning? And can we derive measures that will improve prediction for reaction times? Now, if we think about models for the mental lexicon, many of them are very static. So interactive activation models don't consider learning at all. They look at a state of the system that has arrived due to learning, but the learning itself is not a topic. With deep learning models, the situation is different. These are learning models, but the way they learn is strange from a cognitive perspective. They are trained on many, many epochs through the whole data set, like reading Moby Dick 10,000 times. And after that, yes, you know a lot about Moby Dick. But we normally go through life, we say hi and good morning, but we also do a lot of other stuff. Then the deep learning models typically train on the data until the loss function reaches a nice minimum. But then all the weights in the network have been so fine-tuned that it's very unlikely that we're going to get enormous differences in the weights just by listening to one or two extra words. So if our mental lexicon is continuously being recalibrated in a never-ending process of learning, then maybe we should be able to model that. Now we have two ways in which we can estimate these mappings between meanings and forms. The one I have already talked about. This is multivariate multiple regression. We can look at that as a characterization of the end state of learning. But we can also do incremental trial-to-trial learning using the Widrow-Hoff learning rule, which is the continuous analog of the Rescorla-Wagner learning rule that is studied a lot in categorization behavior. So basically, we can either do incremental regression when the data trickle in step by step, or we can, when we have all the data, then we can use that and then get very good estimates. But they basically are estimates for what you would get if you have endless learning. So, you know, an infinity of years to learn everything about English, and that's the end state that you get with the regression equations. So we have used Widrow-Hoff. But the problem, if you want to work modeling subject behavior, is that the subjects come into the experiment with a lot of knowledge. They are not blank slates. They already know your language. They know English. So what we did is we've first created a network using the end state of learning from basically the words that are in the experiment. And then after that, we started the incremental learning for every trial as subjects went through the experiment in exactly the same order that they got the trials. We now send our model through the experimental data. And for every trial, we first extract some measures like, you know, how dense is the region where a semantic vector arrives? How uncertain are we about the form vector given its meaning? How good is the form vector and the form vector you would expect given the meaning? And we also assume that there is some orthographic learning going on for whether you should say yes or no in this task. Once we have extracted all these measures, then we update the networks with the Widrow-Hoff learning rule. Now, there are also lots of practical things we have to think about. For instance, the training data. What we decided to do is we developed the measures and our regression model for the first two subjects, which jointly cover all the words that are there. And then we said, okay, now we're going to use all the other 76 other subjects and use those as test data. See how well do our measures and our regression model perform for all these held out subjects. Then we basically can compare three models. We can take the classical model that has frequency and neighborhood density and length and all these kind of predictors. Then we can take a model that uses these predictors that are derived from our mental lexicon model, but we don't let it learn. So it's a static model, but it uses our favorite predictors. And then we can take the predictors from our model, but then we let the model learn from trial to trial. Now, if we do this, then what you see for both words and for non-words at the bottom is that the models that, if we take the dynamic models, it's the dark green dots, and we compare them to the classical model, then you can see that the difference in AIC is invariably huge. So the models just predict reaction times much better if we do the dynamic updating. If we compare the static NDL model, so our favorite predictors, but we don't do any learning, then you get the light blue curves. Yeah. So it looks like there is also an advantage to our predictors, even if you don't do learning. And if we compare the dynamic model to the static model with LDL predictors, then you get the red dots. And you can see for the words, there are somewhat more dots, red dots below the line than for the non-words. Now, there is a lot that I could talk about, but given time constraints, I'm going to wind up. The conclusions from this modeling study are first that indeed our mental lexicons may well be recalibrated continuously as we use our language. And the second thing is that this Widrow-Hoff incremental regression learning rule, which is from the early 60s, Widrow and Hoff were physicists, that this can actually be a useful tool for probing continuous learning. So we have all these connectionist networks, deep learning networks. They do wonderful, great stuff from an engineering perspective. But for human cognition, we need something that is much more susceptible to trial learning. And this rule may give us a step in the right direction. So my concluding remarks, this is my last slide. First point, by using distributional semantics and high-dimensional form vectors, we can obtain more precise predictions for the phonetics of speech. We can parse the word embeddings that we get from our colleagues in computer science into component vectors. But when we do so, we may need to keep in mind that we can see interactions of inflectional features with the semantic class of the lexeme. And actually, we have research going on Russian and Finnish at the moment, where we see that how the plurals are realized depends on the case. So nominative plurals have shift vectors that go in different directions than, for instance, accusative plurals. And then finally, the high-dimensional representations of form and meaning in combination with a flexible learning rule, such as the Widrow-Hoff learning rule, make it possible to capture aspects of trial-to-trial learning. Thank you for your attention.
Many thanks, Harald. It's a quite interesting talk, very provocative, very insightful. Before giving the floor to the questions of the audience, I'd like to start just to start the conversation with two questions that go maybe from one extreme to the other. So a very general question, very Socratic question for you is how you relate your work in how you see your work in the wider spectrum, in the wider context of science in general and cognitive science, how you see your work in this context of artificial intelligence, deep learning, and all these many venues that are really promising and already giving really nice results. For instance, I remember last year the award for the most insightful award was given to artificial intelligence working on proteins. So it's like decoding proteins that by hand, by human contributions, it was really slow. I mean, last year, 2021, was a huge improvement on the coding of proteins. So how do you see your work in this, in the realm of contemporary science? That's I think that would be really interesting to see what your take. And the second question goes to the other extreme of our work in linguistics. So we have a lot of folks coming from fieldwork linguists. So we're followed by field workers working on languages for which there is no CELEX. So all these nice results and research based on frequency that is really inspiring. What would you tell this linguist about this? How can you sort of inspiring how, because clearly there is a challenge of a linguist working on languages for which there is no resources, but which, however, can really contribute a lot to this comparative work that we may wish to have. So if we really think that some of these results reflect something of human cognition, we may want to see something reflected in other languages, not only in French, English, Russian, and so on and so forth. So why don't we start with these two questions?
So I have a lot of buttons to touch with us two in the same room. So, okay, your first question, machine learning is making enormous advances. They have great engineering techniques. But what worries me, for instance, with the word embeddings that we have, is that you have to train them on every written word in English for them to work. And I'm happily using them as crutches in which to make some progress, but I don't believe that the way that we learn word meanings is by going through more words than anybody can ever read in 10 lifetimes. Yeah. So what I find surprising is that we work with this very simple linear mappings between form and meaning, and it already works so well. And this is also something that I regularly talk about with my colleagues in machine learning. Is there something out there that gives us the flexibility of human cognition? Because the neural networks that we have are so trained to perform well on particular tasks, but on so much data and so fine-tuned that I think that this flexibility is gone. And big questions for me is, how does this kind of flexible learning, maybe we have this flexible learning and, this may be hippocampal learning, and then maybe there's transfer to more permanent knowledge that is then in the cortex. We don't know. But what we do know is that from human processing, there is a lot of learning going on. And even, over our lifetime, we keep learning words. It's not like we have a fixed lexicon, and that's all. We see that at least up till 70, the works by Colliers and Brisbaert with crowdsourcing for a tenth of the population of the Netherlands, and you can just see that even people who are 70 are still learning words. So our lexicons are not fixed, and so that's more like the general science. As linguists, I feel that we should be able to have something that is precise, that can be learned in a lifetime. And then we should never forget that the constructs that we're working with, like these semantic vectors or these embeddings, that they are far from perfect. Yeah, but it's better than just the meaning of life is life in capital letters. Then, as to field work, there I think a lot of our standard descriptive apparatus is actually quite good. But to give you an example, to go back to this example of apples, oranges, and the plural in English as something that varies with the semantic class. If you go to Bantu languages, then you have all these nominal classes. Class 1 is a singular class for persons, and class 2 is a plural class for persons. And then you go to class 3 and 4, and you have your fruits, and you have your animals, and then you have your artifacts, and you have a waste paper basket class for stuff that doesn't fit in any of the others. And this is a language where they have clearly grammaticalized some of the things that in English exist under the hood. So in that sense, I think that this kind of research that we do with semantic vectors can help us understand that what's going on in English actually is not that different. It's just that we have a slightly different perspective. I think that somebody like Johan Bresden would call these hard constraints as soft constraints. That there are things that, if you make it into, if you grammaticalize it, then it becomes, this is how you have to do it. And in English, it is just not done explicitly, but it is there nevertheless. So that is one aspect on the field work. The other aspect on this is that if we don't have semantic vectors, then we can simulate them. And I think that is, again, a kind of work where, we've started doing this and yeah. So for instance, I've been doing a little bit of work on the Hebrew Bible. So I'm interested, do these mappings work for a complex non-concatenative morphological system? So I have the whole Old Testament computerized, and I can set up mappings very well with simulated semantic vectors, where I say I simulate something for tense, for aspect, for number, for person. If I try to build these word embeddings from the text in the Bible, I don't get very far, because that's 300,000 words. And that's not enough. You need at least something like 10 million to get anywhere. So for this language, it will never be possible to have good empirical bottom-up word embeddings, but we can then simulate them. And then, of course, the question is, how do we simulate these things in a linguistically respectful way? And that is still very much an open question. So in terms of fieldwork and so on, I would say it's challenging, because minority language, the audience should know that Heriberto and I are trying to look at how well the model works for PAMI languages, and as a memory, it works fine, and it right now struggles with being really as productive as we would like it to be. But then we are working with simulated vectors, and I'm sure that we're doing a lot of things wrong. So this is also, I think, an area we will have continuous cross-fertilization. Okay. I will mute and if I can.
Great, thank you very much. That's very inspiring, I would say. So I'd like to ask Sergio Dominguez, do we have questions from the audience on the YouTube channel?
No, none whatsoever.
And you yourself have some questions, comments?
Well, it's a complicated topic, but maybe what I would like to ask is kind of a very basic question, but how can someone like me try to apply this to, for example, the study of negation in any given language?
Okay.
I'm good. So I cannot give any concrete good answer to this question. If the first things that come to my mind is your negation expressed morphologically? Yeah. If so, you might have different rival exponents for expressing negation. If you are working with a language that has, semantic vectors for it, a surprising number of languages now have those. Fasttext makes available vectors for some 150 languages. So there's quite a lot that we can do now. And then you can use these kind of methods to see whether perhaps there are some semantic differences between the different rival affixes for negation. Now, if you think about negation in the context of sentential negation, then what my dream is, but thus far, we're still struggling, making some progress, but still struggling very much, is that it would be nice if we could move away from just talking about single words. So all that I talked about today, this afternoon, is about words out of context, isolated, simple words. But we know that all kinds of beautiful things happen when words are appearing in context. they can reduce in marvelous ways, but also their meaning comes into their own. If you take an example from Elman, English cut, you can cut trees with an axe, and you can cut your finger with a knife, and you can cut paper with scissors. And if we go to my native language, Dutch, then there are 3 different verbs for this. In English, you think cut is all the same. Well, yeah, no, it isn't. And what cut means depends on the words in its context. Now, our context vectors, our semantic vectors, are capturing some of that, but still they work with just the isolated words. So you might want to go to these newer methods where you have word embeddings that are completely dependent on the context, using these models like BERT and GPT-3. But ideally, what I would like, and I don't know whether it is feasible, but I would like to think of an utterance or a basic kind of thing that you want to talk about as a point in a high-dimensional space. So that it's, or at least something like a verb phrase, like, cut with scissors, or, kick the bucket, either literally or non-literally. If we can think of having a high-dimensional representation for a sentence or a short utterance, then we can start thinking about how that whole thing is then realized in form. And if we can find a good way of doing this, then that might give us much better insight into also all the aspects of the lexicon that people like Jack and Dove have been talking about for years, and that it's full of all kinds of idiomatic expressions, collocations, ways of saying that we all accept as completely logical and that are a pain for second language learners to master. So, and of course, in computer science, computational linguistics, people are also now, generating at some point semantic vectors for an utterance, and they do it all on the basis of next word prediction. And I think that for us as linguists, it's very interesting to think of, if we take our whole conceptual toolkit from aspect and tense and modality and evidentiality, and we bring that all together, and then we try to do what I was trying to do with some of the morphology, then we might get much more insightful representations. Or maybe we could take the sentence representations that our colleagues give us for using deep learning methods. Maybe we can decompose them in a linguistically sensible way. Because after all, we want, as a scientist, we want to understand what's going on. And a lot of the work that's been done is engineering work. It's very smart engineering, but it's not aimed at trying to understand why things happen. It's just aimed at, or at the very noble goal of making things that work. And they are very, very successful. And I think that our challenge is to make sure that we understand why they get so far and how we can get equally far without needing these huge data sets. But that's maybe a bit presumptuous, given how far they are.
Thank you.
You're muted. Sergio, you're muted.
Sorry. Thank you very much. Thank you.
Hola, Sergio.
Sí, ¿no me escuchan?
¿Querías decir algo?
No, solamente dar las gracias, Moe. Thank you very much.
Great. That's really nice answer, because you basically are calling for an international collaboration between all linguists of the world to contribute to this. It's in some ways is the World Atlas of linguistic high-dimensional typology or something like this. It's great. So, but on the other hand, so that the answer also triggers to me this phrase. I don't know if this is already on the market, but I would say all models are wrong. some of them are more useful than others, which is a little twist on that. So Sergio, do we have any other intervention? So I saw people attending from Brazil. So some colleagues from Brazil are attending, so maybe it's early for them. Go ahead, Sergio.
Oh, thank you. Yes, no questions whatsoever.
Well, if there is no any other intervention here, so Harald, would you like to say some final remarks on anything, or greetings, or?
Well, yeah. So no, I think that I'm grateful for the opportunity to talk about this, and yeah. My hope is that the kind of modeling that we are doing is useful, and I think the most useful thing is not the model, but the idea that we can get very far if we start using these word embeddings when we study linguistic form and meaning. And we have to have better word embeddings, we have to get better resources, but I think that this is a useful thing to do, although it will undoubtedly change very much as we learn more.
Right.
Thank you.
Thank you for this really nice, exciting talk. I'm sure people are just inspired and curious about your models, your proposals, and who knows, we may have some calls and some interaction with people later on. So on that note, so I like to say bye to people, and thank you for your attendance. So we'll see each other in the same channel, not same time, so we have to change it somehow. Next time, thank you very much to the team at the National Institute for Anthropology and History at the coordination back in Mexico City, and all people who attended this talk. Okay, with this, we're off. Thank you very much. Bye-bye. Stay safe.
Gobierno de México.